Hi everyone. In this video, I'm going to talk about a Bayesian method to estimate the log PSD using B-splines with applications to LISA data. My name is Patricio Maturana, and this is a work, a joint work with Petra, Jan, Nelson, and Renata. So in this presentation, I will talk about the Bayesian method to estimate the power spectral density function, and then I will show you some applications. So the power spectral density function is the Fourier transform of the autocovariance function. And this function is used to model the stochastic gravitational wave background and also the instrumental noise. So that's why it's important, its estimation. So in this presentation, I'm going to talk about Bayesian method to estimate it. The advantage of the Bayesian method is that they yield full distribution of the parameters. And the disadvantage is that they may be computationally expensive. So a few methods have been proposed to estimate this function in a Bayesian way. So we have the Bernstein method, the B-spline, and the P-spline. Here, I tested the methods in a case that we know the analytical PSD, as which is the case of the autoregressive model of order 4, in which the PSD is given by this continuous line. As you can see, the Bernstein method is not flexible, it's not able to capture the second peak of this PSD. The B-spline method is quite flexible, but the problem is that it's computationally expensive. And the P-spline method is quite flexible and also is less computationally expensive. So we proposed the P-spline method in 2021. The three methods use the Whittle likelihood. So in the P-spline method, we allocate as a prior a mixture of P-splines. The P-splines are combines the B-spline bases with discrete penalties on the basis coefficients. So in our method, we assume that the number of nodes in the B-splines is fixed. We also assume fixed node location, but we allow to consider non-equidistant nodes and also equidistant nodes. And we found that non-equidistant nodes works much better than equidistant nodes. And then we assign a prior on the weights. In this proposed method, in the method that we are going to propose today, instead of estimating the power spectral density function, we are going to estimate the log power spectral density function. So we estimate this parameter plus the log of this part. And also, we are going to use a parametric auxiliary model to gain efficiency, which is discussed in this article in Kirch et al. 2019. One of the advantages is that in our method, the weights are not restricted to live in the interval 0, 1. So we assume as a prior, we assume that the weight follows a normal distribution, and the covariance matrix in this case is composed by a penalty parameter and a penalty matrix. Then we assume a gamma distribution for this penalty parameter, and here we consider a hyperparameter in the right parameter of this prior, which also follows a gamma distribution. The idea is to make the posterior more robust to prior specifications. We want the posterior to be dominated by the data and not by the prior. And we assume a normal distribution for the log tau. So if we assume this prior distribution, we have analytical solution for phi and for delta. And we are going to use an adaptive metropolis hasting to estimate the posterior distribution of the weights and log tau. And now I will show you some examples. So we estimated the PSD in the case of the autoregressive model of order 4. And we can see that our method is able to capture both peaks of this PSD. The shaded area is given by the credible interval of the posterior distribution, the credible interval for the PSD, which is determined using the posterior distribution. We also estimated the PSD for some of the data sets available from the LISA data challenge. And here we estimated the stochastic gravitational wave background given by a power law, but without considering noise. So we take a subset of this data set and we estimated the PSD. And as you can see, our method is quite flexible for this kind of shapes. We also try our method, but to estimate the stochastic gravitational wave background plus noise. And here we can see that our method is quite flexible. So because here we are just in an early stage of this work, so we are interested in testing the flexibility of our method. And finally, we apply our method to estimate the PSD composed by the PSD of the stochastic gravitational wave background and also noise. As I said, this is a toy example. So in this case, we consider a power law for the stochastic gravitational wave background. And for the noise, we consider autoregressive model of order 4. So we consider 1,000 time units and a sampling frequency of 25. And then we generated the data. And we estimated all this PSD, the PSD composed by these two PSD. And for the power law, we consider the parametric model. And for the autoregressive model, here in this part, we allocated our method, the B-spline, the log B-spline method. And this is the result. So the black line represents the true power spectral density function, and the red line represents our estimate. So this estimate. The dashed line here, this one, and this one, represents the autoregressive model, the PSD of the autoregressive model, and this one represents the power law. As you can see, there is a tiny difference between our estimated power law and the true power law. And the estimated noise, it follows the shape of the true PSD, but probably we can improve our method to get better estimates. As I said before, these are preliminary results, but this gives us the idea that we are in the correct track. So as a future work, we want to speed up our algorithm, and also we want to try our algorithm in more realistic scenarios as the one described here in Caprini et al. 2019. So thank you for watching, and here you have the references of this work.